So today the theme will be instabilities, and I hope to get to the point of talking about why we really don't know if some instabilities that we think should work and operate in neutron stars, if they are actually active in real neutron stars or not. So that's where I want to get to. I've got to cover a lot of ground. Some of it is going to be a little bit on the mathematical side for a bit. You can fall asleep then if you want to. But I think it's quite important to understand both the history and some of the machinery that you need to use if you want to really understand these things at a deeper level. Okay? But I'm going to start by talking about something that really laid the foundation, and that's the work by Chandra on ellipsoids. And so this is pretty much going to explain, in a way, everything, or much of what comes after, and much of the work that people did later. So Chandra's work was early, in the 70s-ish, 60s, 70s. And the work from, in particular, John Friedman and Bernard Schutz. There's a sequence of papers starting in the early 1970s, culminating in 1978. The famous papers are from 1978. There are two of them. Many people in this business would cite these papers automatically without, I believe, having actually read them. The most interesting papers, in many ways, are not the papers from 1978, but the earlier papers leading up into this. Because if you read the whole sequence, you can see how they struggled with the ideas and what they were trying to do. And then finally, and actually John Friedman and Bernard Schutz separately wrote papers leading up to this. And you can see it's only when they combine their forces and come together and join their thinking that these papers, which are really masterpieces in some sense, or also confusing, but okay. They are fantastic papers, but you can see that when they come together, that works out. Okay. But I wanted to start drawing a diagram and talking about this diagram for some time. So I'm going to draw a box. I don't know why I'm drawing a box, but why not? No, I'm not going to draw a box. Draw it like this. So I'm going to draw this axis here. It's not going to have any labels on it because I think it will be confusing. But what I want to draw is a book. It is a diagram for rotating homogeneous, so uniform density bodies that are not necessarily, spheres, so ellipsoids. And this axis, in some loose sense, is the ratio. If I rotate with respect to the three axes in my body, so that this is the three axes, this is the ratio of the other two axes, A2, A1, whatever, and it grows in this direction, and it also grows in this direction. Okay, so it's kind of a funny diagram. And then what I want to do is I want to quantify this in a variable I'm going to call beta. And this beta is a measure that says I take the kinetic energy, which I'm going to call T, and then I take the ratio between this T to the absolute value, because this is negative, the potential energy. Okay, so this is a measure of how much rotation you've got. You would think perhaps it would be more natural to write down something like a rotation velocity, right? But for the diagram I'm drawing, that's not such a natural measure, because we will have systems with differential rotation on this plot. So then that you can still measure these energies and get a sort of number, okay? And now it's useful for your reference that you calculated for me in splendid fashion yesterday the breakup velocity for a neutron star, and you came to an answer about a kilohertz, thereabouts. Now, in this measure, just for our reference for later, if you worry about such things, then that's going to sit at some value here, which is about maybe say 0.1. I'm just putting that there in order to relate what we did yesterday in the tutorial to what's happening in this diagram. Okay? Now you're going to immediately ask, well, why have I drawn this line above this point? Because clearly you demonstrated yesterday that no star will spin faster than this, because if it does, it will throw the matter off of the equator. So you can't go higher than this. Okay? But the assumption in the ellipsoid case is you don't worry about that thing. There is no such thing as throwing matter off of this ellipsoid. The matter is locked into it. Okay? And you just ask, how fast can I spin this thing? Okay? Okay, so the first thing we need to do is we need to give a name to objects that live on this axis. Okay? So, uniform that's when these we have just centrifugal type deformation, so these axes are the same. Actually, it's probably decreasing this way, but it doesn't matter. Right. So they're equal to 1 here, and then decreasing this way. So you make one of them bigger than the other. So these guys are called the Maclaurin spheroids. We're going to go through some classic names in mathematical physics in a way. Okay? So this is this sequence here. The two axes are the same, so it looks like a rotating, flattened sort of thing that if you keep on going, it becomes some sort of pancake, right? Circular pancake. But then what you find is, if you try working this out, you get to a point, let's say 0.1, say 0.14, a very important point where there is a bifurcation of this sequence. And you have a branch off to another guy, another set of guys over here. These are called the Jacobi ellipsoids. Again, Jacobi is a famous name. So these are different, see, because these have got not the same value of these two axes. So they got all the three different axes in the body are different, right? But, so we need to figure out some way, how do we do that? And the way we can do it is by introducing some kind of differential rotation. Okay? So put in some either internal velocity field or let it push it some other way. Okay? So these guys rotate around that three axis as before, but it's only when you look at them in the rotating frame, if you rotate with them, that they appear stationary, which means that they have some kind of differential rotation, okay, in the inertial frame. Basically, these have lower energy. That's going to be important than these guys, but no circulation. So there's no internal flow. Okay. And then there's another way I can do this. I can break this way and go off to something called the Dedekind sequence. These guys achieve different axes here by having internal circular flow, right? So you can get this set up by basically saying that I let the fluid inside move differentially. Okay? So these have internal motion. And because they have internal motion, they have circulation. And they have essentially the same energy. You can arrange it to have the same energy as these guys here. Okay? Well, I've drawn this diagram for the simple reason that when I get to this point, if I try to march on along this uniform Maclaurin sequence, right? Once I get above this point, it would be cheaper for me to move over here because I can find a lower energy state with the same angular momentum. Okay? So provided I can find some way of losing energy while conserving angular momentum, I can move over here. Okay? And that means effectively that this sequence, the Maclaurins, is not stable if you introduce some extra piece of physics. So if I put in viscosity, right, what does viscosity do? It lowers energy. Viscosity will drive me this way. So, and because we need to put in some extra physics, and the rate at which this instability proceeds depends on how fast this physics mechanism is called a secular instability. Secular here means simply associated with some other time scale. So viscosity is an example. But it's a way that you can go from the Maclaurins to the Jacobi sequence. Okay? And this is a classic, a very classic result. Which point? What you need to add? Okay, why you get it? Or, okay. Well, so you can just imagine you're trying to sit here, but this is the top of a ridge, okay? So it would be very nice for you to stay down here, because this is lower energy. You need to work less to go down here, okay? Or a cheaper live, right? But you need to figure out a way of spending the excess cash you've got, right? So if you find someone that, say, asks you to pay tax at a certain rate, and you call that guy viscosity, because viscosity saps energy from the system while conserving, then you can move down here, okay? And in fact, if you put any such mechanism in, you have to move down there, right? So that means that this branch here is not stable. You would have to set the system up in a very specific way and avoid all viscosity to continue up. Okay, so a real system will not be able to do that. But then you have to ask, okay, what rate of tax is it? Am I living in my home country, Sweden, which is the highest tax country in the world? Woohoo! Or am I living in a country where tax is illegal? And if I live in the tax illegal nation, which would be a bad place, there wouldn't be the hospitals and schools and stuff like that, but don't worry about it, then I can carry on. If I live in Sweden, I go down here immediately. Okay? Yeah? So now you can ask, okay, well that was one way. Now, how can I go down here? Well, that would also be cheaper, but now I have to find some way of going that conserves circulation. Okay? Now viscosity doesn't do that, what gravitational wave emission does. So if you have, because this is a body that is deformed, it will rotate gravitational waves, right? Well, actually not here, it is not, but if you just perturb it a tiny little bit, right, then it has different axes here, so it has one of these epsilons we talked about, and therefore it will have to go. So as long as you fine-tune it, so it's perfectly symmetric, it will carry on up, but if you just kick it a tiny bit, that gravitational wave deformation is going to kick it off, and it will fall down to this branch. So, okay? Yeah, so you have to conserve circulation along the path. So I don't usually talk about circulation in gravitational wave sense, right? But you can show that gravitational waves conserve the circulation in the flow, and therefore that's the path you're going to follow. So what we're learning this, I love this diagram because you're learning a huge amount from it about the ideas that come in, okay? But it is messy. So we learned that this guy, the Maclaurin guy, is sensitive, okay? You don't have to push him very hard for him to fall apart. But let's suppose, just for as a thought experiment, that I carry on bravely anyway. I don't have any viscosity, and I avoid deviating from this perfect symmetry. I carry on marching upwards. How far can I go? Will there be an end? And yes, there will be an end. When you get to about twice this, about a 0.27, that's basically the end. We have a dynamical instability, and here dynamical means that it will happen even if you don't have gravitational waves or viscosity. It just relies on, if you like, the equations without any extra forces, okay? And at that point, this body that was symmetric will deform into a bar on its own without any extra. This is called the bar mode instability. Okay. And in principle, if that instability acted in real systems, this would be very interesting because it grows very quickly, deforms the system into a rotating bar, essentially. You've done calculation for rotating bars. You know they radiate gravitational waves, right? So if it grows like that spontaneously, that would be very interesting, right? Of course, you can see from my diagram that might be tricky. It might be tricky to get there. So how do you get a real star up to this kind of thing, where I've said it's actually difficult to stay there, okay? So one idea could be that you get this in when a star is born in a core collapse. So for some reason the collapse is such that you get a whopping large amount of angular momentum, so this value is large from the beginning, and people have shown indeed as a supernova collapse proceeds, you get up to this threshold in some situations, so you trigger this instability, okay? But unfortunately, what happens next is that you hit the high density region, you get what they call the core bounce. So then the system expands again. So you trigger this instability and then immediately quench it by having the growth. So you can get this in core collapse supernovae, but it might not have time to do anything, okay? Another situation where this can happen is in neutron mergers. Because now you're taking the two stars, whacking them together, there's a lot of angular momentum here, and actually the system naturally forms a bar anyway. I'll show you some, that's going to come tomorrow, some snapshots from simulations, but essentially you can imagine taking the two stars, they go around one another, when they come together that looks like a bar in some sense, okay? And that could also be above this threshold. So people in numerical relativity have looked at this quite a lot, and there is a very simple reason why they do that. This is a simple simulation to do, because you don't have to add any fancy physics. The fluid will do this on its own. So you have to just set up your code, whatever it is, so that you have a body rotating fast enough, and this should happen. And for some time, people thought this could be quite a good gravitational wave mechanism. Now I think people are not so convinced, because it turns out that, similar to the mechanism we're going to talk about later, there will be other modes that interfere with this and basically stop this thing from growing, and means that it doesn't last very long. And you remember when we talked about rotating deformed stars, the signal itself is weak, so you need to have many cycles to make this detectable. And so if you disrupt this thing before it builds up these many cycles, you don't win. Okay? So it's not clear, certainly not in my mind, whether this is we're actually going to see this kind of thing in reality. But it could happen in principle. Okay? Okay, so now I talked a lot about this. You're thinking, okay, but real stars not. Yes? Yes, that's right. So over here, you still have uniform rotation in a sense. But over here, you have still have differential rotation if you look at it from the inertial frame. And over here, you have internal circulation. So there's an internal flow. I could have shown you a picture. I can't remember where I've got it anyway. But it's got sort of little arrows, or the velocities going around at different rates. So it's like a football, American football, rugby ball, whatever you like, with internal flow. Where are we getting it from? Those numbers, or how do you calculate it? The T is the kinetic energy, so just the rotational kinetic energy. And of course, if you got differential rotation, internal rotation, that's a bit more complicated to calculate. The W is just the gravitational potential energy. So that's it. Okay. So you might wonder if this has any connection with what we've done or what you've done. In fact, it does. So let me show you this diagram. So here is a rather complicated plot, and I want to talk about this one for a little while. You could start asking, okay, what is the relation between these deformed ellipsoids and the stability here and the modes of the star, right? So we looked at the F mode, the fundamental F mode, yesterday, and it turns out that there's a very close connection with between this picture and the calculation that you did. Okay? So now we need to just ask a different question. What happens to the F mode if we rotate the star? Well, first of all, we saw already that we had some frequency that went like L or M, and we know that this is going to split up into two. Let's do M. When we take the square root, we've got a +1 and a -1. And then we looked at that pattern speed, which is minus omega over M, in a non-rotating star. This is a general statement. But if we add rotation, then we need to add or subtract, depending on what frame we're using, an extra piece that just says that if we rotate, there is an angular bit that comes in when you go from the rotating frame to the inertial frame. And then there's also going to be some other bit that we don't know, which depends on what kind of fluid it is. So this is just translating the frames. Okay? And this piece is saying, well, depending on what the fluid is, it's going to react to the rotation in different ways, say through deforming in some, depending on how compressible it is and so on. I don't know what that number is, because what that function is. We know that centrifugal deformation comes in at omega squared and so on. I'm not going to worry about it, okay? So in this diagram, I'm showing a number of things. Up here, is one of those modes, the +1, say, and down here is the -1. Both of them have two branches. You can essentially think of this as a complex thing for two of these, but then, so this is for one value of m, but I have the opposite sign of m, that gives me another pair. Okay, so I can think of either the two of them, so really there should be one of them and the other one down here correspond to the same value of m, and then the other ones are the opposite. Okay, so there's a symmetry in here. And then you see what happens. This is, I spin the star up in this beta. Okay, one of them, let's take the top arc, goes up a bit and then it bends down again. Right? The other one is this one, goes up and it goes through 0. Okay, it goes through 0 at this value here, which you can probably eyeball, is 0.14. Okay? Now let's trace what happens next. It carries on up and it meets that first guy. They come together and suddenly there's only one line here, and that is because this frequency of the F mode becomes complex. And so here is the imaginary part, and you can see it picks up an imaginary part, positive and negative, but because we have assumed e to the I omega t, if you got a guy with a positive imaginary part, that's fine, because that's going to decay, but a negative imaginary part here is going to be unstable. Okay? So in this diagram you see the bar mode instability here at 0.27, and you see this point where it changes sign. Okay, so this is where you could have that first bifurcation, and here is the bar mode instability in the F mode of a star. Okay? Here's the same plot for just one of the pairs, but not in and in beta, but not in frequency, but in pattern speed. And that's just to show that this pattern speed that I drew changes sign here. Okay? So this is a little bit harder calculation than one we did, but it extends what the stuff that you did to rotation. Okay? And it connects as well the mode picture with this ellipsoid picture. Okay? So that's a big step. So now what I want to do is I want to write down some stuff. I have no idea how long this is going to take. It could be all day. But I want to write down a piece of mathematics that proves rigorously why we have these two instabilities. Okay? And that's going to give us something that I kind of already know now. So this next exercise would be a complete waste of time. Okay? Apart from this is the machinery that you have to use if you're going to do these kinds of problems. Okay? And even though it's not clearly spelled out in all the papers, this is what everything builds on. So this is a masterpiece. This first thing was a masterpiece of Chandra, and this next piece is Friedman and Schutz, what they added to the picture. So we already see what's going to happen. At 0.14, the pattern speed changes sign. What does that mean? It means that a mode that started out going backwards or forwards, it started out going backwards, is now dragged forwards by the rotation. Basically, imagine sitting on a non-rotating star. You have two F modes, one goes this way, one goes that way. But it doesn't matter to you this way or that way, because the star isn't rotating. You have no reference direction. Okay? Now the star starts rotating. Suddenly, the mode that goes backwards will appear to you to go a little bit slower backwards, right? Because I'm dragging it forwards this way. And then, when we get to this 0.14, that F mode will now appear to you to be forwards, but to me to be backwards. Okay? So now let's ask the following question. Let's suppose this guy radiates angular momentum. Okay? Because you see it going forwards, clearly for you it will radiate positive angular momentum because it's going forwards. Right? But for me, I'm sitting on the star, it's going backwards. You're taking away positive angular momentum. me, it's negative already. So you're taking something positive from something negative. I'm now in more debt than what I was before. Right? So the amplitude of this mode will grow. Okay? That's the picture. So that's why this pattern speed change is important. So what I want to do is I want to sketch, talk a little bit about the machinery, and then sketch how you prove this. And this is, I think, certainly for me, because I'm a little bit, first of all, I'm very sloppy, and secondly, I'm marginally incompetent. So when it comes to calculations, I always have to do things 100 times. And so for me, going through this calculation, not with you now, because this is, now I know it, but the first couple of times, this was hard, okay? So don't worry if you think, I never want to see that again, okay? That's natural. But you can't leave because we've locked the door, right? So what we're going to do now is a little bit closer at the concept that I wrote down before, but now we're going to try to make it precise. And we need to do that for a very specific reason. And I will explain that. So we're going to take a quantity Q, it can be anything, and we're going to define the Lagrangian perturbation, the one that sort of goes along with the flow, right, as this Eulerian perturbation, which is at a fixed point, which we used before, and a piece that says that we take the Lie derivative along a displacement vector, so the difference between these 2 points, where I am now and where I was before, of Q. So how many people are familiar with Lie derivatives? Hands up high, please. Come on, don't be shy. It's not a shame. It just means that you know a little bit more than I do. That's okay. Okay. So I'm not going into this, the differential geometry of this. That would be kind of pointless. But if you want to think about what I'm going to write down, it is sort of have a mental picture. I think the best mental picture of the Lie derivative I have is from the mathematician Arnold. Called it the fisherman's derivative. Okay? So you can imagine there are 2 different ways of taking derivatives. There's a river, and you can stand on the side and do your fishing. That's just the normal derivative. You look at the flow and see how it changes as normal derivative. Or you can do your fishing from a boat that flows along with the flow. Okay? That's the Lie derivative. So why do I use this fancy thing here? Well, I use this fancy thing here because if this Q is now a geometric object, not a scalar, a vector, a tensor, something like that, then it will now suddenly depend on, it will make a difference if it's co or contravariant and so on. I need to be careful about the geometry because the way I drag the coordinate systems depends on this flow. Okay? That's why we have to make this distinction. Okay? So what happens, I'm just going to write it down. If you have a scalar, then this delta f is just, no, well, let's just do the Lie derivative. Then the Lie derivative of f is just the vector xi contracted with the gradient of f. This is what we used before, because we used it for the pressure. Right? If you have a velocity field vi, say, contravariant because it's a vector, then this guy is the same, vi, sorry. The same piece, the one that's easy to remember, you just put the vi instead of the f, but it has a second bit, which is not so easy to remember, and then it has a minus sign, and you know what happens with minus signs. I put one into the exercise yesterday where I shouldn't have, so that's what happens to minus signs. But it has the same form, so it's also easy to remember. Just take exactly the same thing, just swap over the xi's and the v's, okay? And you learn something immediately, that if I take this derivative along v of v itself, this is going to vanish because this becomes Vj grad j Vi, Vj grad j, this is 0. Okay? Now we'll squeeze in the covariant down here. So that sounds easy, but unfortunately this Lie derivative acting on the metric that would lower this index, even the flat space-time metric, is not 0. So that messes up what happens to the covariant object. Okay? Still has the same first piece. This is always the same. Whatever the object is, whatever number of indices you have and so on. But then there's a plus, and this second piece is a bit messy. It still has a v, but now the index, the free index, is on the derivative. Okay. And this is simply, essentially you can now figure out for me, it could be your exercise, figure out what is the Lie derivative of the metric, right? Because you know this is lowered by a metric, so you can work out from the product rule what would that have to be for these two to be consistent. Okay? And now you see why this becomes much, much harder to work with. Okay? Because you need to keep track of, are we upstairs or downstairs? It's not just simply saying, oh, we've got covariant derivatives, so through as I like. That's not the goal, because the metric is now affected by this. So this is important. And because I'm doing this with ij indices, because I'm going to work in 3 dimensions at the moment, that is not 0. Okay? Whereas the beauty of covariant derivatives in relativity and flat space, whatever, is that whatever metric you've got just goes straight through. Now we need to worry about it. And you can see, if you're familiar with any relativity calculations, that this is not going to be useful. It's going to be terrible. Okay? So now we have everything we need, in principle. We know how to work out the perturbations of a velocity field and so on. I'm obviously not going to crank through the whole thing. I just want to show you what the essence is. So I'm not going to crank through the algebra. But we can show one very, very important thing. And for a moment, brief moment, I thought that we could do this in the tutorial. But then I had one of my able assistants, have a go at it. And I think you're still working on it, right? I think he will report back before 2 o'clock if this is doable by mankind. And if it's not, then we'll change our minds. Okay? I just thought it would be nice to do something related, and we'll find some version of something that's doable. But it has to be doable sort of within a limited time. Some of these calculations are just hard. Okay? So the reason, one reason why these calculations are not so bad, the ones I'm going to do are not so bad, they're still not so good, but they're not so bad, is you can show that the combination that you can achieve from the Euler equations and so on, namely the time derivative plus the Lie derivative of v of, say, the downstairs object. This is true for all objects, but I'll just take the downstairs velocity field. So this is something I can build now, right? I just put this guy definition, I have it down here, put the v instead of the psi, copy down, I know what this means, right? And now I act with this on this delta. Well, I know what that means. I know I need to take this and then ask, what is this object? How many indices have I got on this object? I've got one free index downstairs. That means I should apply this rule. And now I have to hit this whole object with this. This whole thing goes in there and here, okay? And then the other two are sized, just like that. So I can just almost cut and paste, okay? Then I have to crank through, try to move the derivatives around, and that's the messy part. But if you do that, you can show, allegedly, I have done this, but not today. that this operation, the Lagrangian variation, commutes with this operator. And that means that anytime you see this, you just bring that straight through. The continuity equation, and the first stop is to say, okay, let's get rid of as much as I can. And so I rewrite this as dt rho, or maybe dt plus vi grad I rho, that's a piece. Sorry, acting on rho. And then I have another piece which is vi grad I rho. Okay? And then I go back and I compare notes with over here, and I see that this is a scalar, of course. So this piece here is just dt plus li of v acting on rho. Like that. Right? And now I know if I hit this with this delta, that just goes straight through this piece. So this piece is sorted, and then I just need to worry about what happens to this piece. Okay? So that's one way that you can make use of this, and what happens at the end, which we may or may not work out later today, is just that it works out that this is an overall derivative of an object that looks like this. And that just says that the Lagrangian variation of the density depends on how much expansion and contraction you've got of this vector. Of course, the big job now is to try to work out the Eulers. And I'm definitely not going to do that for you. That will take us a very, very long time. But I want to do it mathematically. So here what you do, the first step is exactly what I said. You rewrite the Euler equations as a piece that has exactly this combination again, but now because it's a vector, or a covector, I use this whole expression. Okay? And then what's left, and you see that this picks up a piece of the convective derivative, and then you're left with the usual 1 over rho grad I p, and then plus grad I phi minus a half v squared, vanishing. So you pick up this sort of kinetic energy piece. Sorry?
There's a slight mistake in the steps you've written there. There's, I think it should be rho del I vi.
Okay, so what happens to this equation? Well, lots of work. But schematically, it's quite easy. It's going to have three pieces. It's going to have some second derivatives of this vector psi. And now I'm not going to put the indices on it. I'm going to be lazy, okay? It's going to have a piece that essentially is the rotation that has a first derivative of psi. And then it's going to have a piece that is a function of psi in some sense. This piece is really easy. It's actually just derivative. This piece is not so simple, because actually what this piece is something like 2 rho Vj grad j of dt psi I. So this is what this kind of means. Schematically means it's some function that depends on time derivatives, okay? And this guy, I'm not going to write down in 100 million years, because it involves tricks with the gravitational potentials and swapping things over, and that calculation is a real mess, okay? But this is what Friedman and Schutz did, part 1. So this is a kind of if you start doing this calculation just for fun, then you think, oh, well, my life is clearly, not busy enough, right? But they had a plan, and the plan was to take these guys and say, take two solutions, these equations, so the perturbed Euler equations, and try to build an energy. And so the way they did that was by defining essentially a dot product between functions. So you need one upstairs, one downstairs, and then this is simply defined as the volume integral of the complex conjugate of the first one times the second one. Okay. So if you know these two functions, you can work this out. And then they show that with this definition, I've got some conjugation rules for these things, so I can show that a solution eta times AXI is the same as A eta times Xi. So that's very, very easy. This A is just rho, right? So in this product, it's just a number. So clearly, I can move that number from sitting with the rho Xi to sitting with the rho. Done. Okay? Similarly, you can show that there's a commutation for B, but it's not the same. It's minus Xi B eta, and then all conjugated. Has to be conjugated because when you do this thing here with the velocities and just one time derivative, that comes out. And finally, the one that's really hard, because this expression for C is really messy, is just that this one is the same as the first one. Or it should be a conjugate here as well. You need to conjugate because you need to move this complex conjugate from one to the other. Okay. So now what I've got a machinery, first for working out the perturbations, and second for building out of this equation some quadratic bits. Okay? And if you want to build an energy, you need squares of velocities and so on. So now that I can build an energy for the perturbations. Okay? So that's what we're going to do. So what you're looking for is some quantity that is constant in time. So something that is conserved. And one way you can do that, given these relations, is to define a guy called W, say, sorry, normal bracket, which is simply that inner product of eta, A time derivative of Xi plus B a half of B Xi, minus essentially shunting that operation to the first one, okay. So why should this be true? Well, what you rely on is the fact that these Xi's and etas are solutions to this equation, right? So when you work out the time derivative here, right? Push the time, these are just integrals in volume, these angle brackets, right? So I push the time derivative through. First I hit this guy, but when I hit this guy, I get A doesn't depend on T, so it's just second derivative plus half of B times this time derivative, okay? But then I know that it's a solution to this equation, so I can use this equation and express that in a half of B and C, okay? And then the same trick over here for these guys, but then and then you end up with something that's quite easy to see that they have to cancel, okay? So this proof at this level is quite easy, okay? But this is a very important result. Because now, you see, I didn't tell you what these two guys were yet. But you see, I can put now in whatever I want. Let's take this Xi to be a solution to this. But because the A's, B's, and C's don't depend on time, I could also put in the time derivative of Xi. That's also a solution to this, right? So what they did was they said, let's build a canonical energy let's call it EC, and let's just take that to be half of this W acting on time derivative of psi and psi. Okay? I know from this proof that this will be a conserved quantity. Okay? So now I have, for the perturbations, a way of measuring an object that's conserved in time. And you'll breathe a sigh of relief in just 2 minutes or something. We're almost done. Okay? These guys, also because this is a rotating star, if I assume it has axis symmetry, then it doesn't depend on the phi angle. Okay? So then if the background is axis symmetric, then the A's, B's, and C's don't depend on phi either. That means I can push a phi derivative through all of this. And so the phi derivative of psi also satisfies this equation. And so I can build a canonical angular momentum, which is simply a half W of partial phi of psi and psi. Okay? And this is also conserved. And now you can ask, what happens if I put in this F mode thing? I know it's a solution to the perturbation equations, right? I can calculate that psi, so I can work out this canonical energy, right? But I also know that I've assumed that it has a frequency, so it goes like e to the I omega t. Well, for modes, you can show that this canonical energy is just minus omega over m times jc. Defined this already. This is that pattern speed times jc. So apparently, so this is result number 1 that we'll need. And we can also show, but this is messy, so I'm just going to give you the result and argue why the sort of intuition comes from it. You can use the angular momentum thing and the mode solution to write down an expression that says pattern speed minus omega times 1 plus 1 over m is always smaller than jc over m squared divided by this kind of thing, which is some number, some positive number, which is also always smaller than pattern speed plus minus another thing, minus 1 over m. So this is always bigger than this because you're taking away less. You're more here than you're doing here, okay? This is a very weird looking expression. Very strange, okay? But now I need to go through a logic that I never get straight in my head myself, okay? But now we're going to prove the statement from over there, okay? The proof is here, okay? So what you do is you first say, what happens if we let the omega be really small, okay? Well, if the omega is really small, then a mode that co-rotates so that this is positive, right? Then basically this is positive. We're taking away something really small, small enough that this is still positive, right? So JC is positive. So if omega goes naught, if sigma p is positive, then JC is positive as well, right? We have positive angular momentum. So if we go positive angular momentum, here, this is positive, E is positive. Right? This is number 2. So now let's ask what happens if we get up to the point where if have sigma p goes to 0 at finite omega. So what happens then? Well, That's the point we've seen over here, that the pattern's been the mode changes from co to counter-rotating, okay? So now what happens? Now this is small, 0, so this is negative, this is more negative, so JC is negative, this is negative, this is small, 0, and this guy will have to change sign as we cross through, right? Because this guy changes sign, and therefore it has to change sign. And if we assumed that the mode was stable from the beginning, which makes sense, we start off with a non-rotating star, then this change says that the mode goes unstable. And that is the Friedman-Schutz proof of the instability of the F mode. And this logic holds for any mode that has finite frequency, so that you can do this pattern speed argument, and you get a change in that pattern speed. And since then, people don't do this, whatever it took me, 40-minute calculation. And of course, I didn't do the meat of it, the hard part, right? Nobody does this, because the masters have told us that the only thing I need to look at is this pattern speed. Does it ever change sign? I only have to have this. Yes, it changes sign here. And then I said, well, some guy at some point in the past showed that this means there will be an instability. This is a simple version, but I think it's very important to understand where this thing comes from, okay? There's a complicated logic with some fairly hardcore calculation on the problem, and this machinery allows you to do much more than just this final statement. All it did was we've derived a fairly trivial sounding statement that you then explain. Remember yesterday I talked about simple pictures, this co-rotating, backwards rotating mode becoming forwards rotation, rotating dragged by the rotation of the star, positive angular momentum, negative angular momentum, the mode has to grow argument. Is an after construction, okay? That comes, once you know this, you come up with that mental picture, and then once you have that mental picture, you don't go back, okay? Unless you make a rigorous proof that a given mode is unstable.
Before you erase this to write something else, can you tell me where is the information that this instability is generic for all objects, regardless of how slow the rotation is? Where is that contained?
Wait, which information that it doesn't?
The information that this instability is generic, even for slowly rotating objects.
Okay. Okay. No, that's a really good question. Okay, so that's a really good question. So now let me erase this piece. Okay? We calculated yesterday that the non-rotating mode frequency went like something like root m for an L equals to m mode, right? Plus or minus. And then you have the minus m omega that you need to do to go into a rotating frame. And then you got some other stuff, which I don't know. But let's forget about this stuff for now, okay? Because I just want to sketch it to you, okay? But then you know you want to look at this pattern speed, which is minus omega over m, right? So let's put that in. That just says that we get a plus or minus root m, so 1 over root m, minus or plus, so minus plus omega. Okay? You need this to change sign at some rotation rate. So you just say, well, it can't happen for the plus root, but for the minus root. So it's going to happen when omega is 1 over root m. But you can make m as large as you want, because it's the spherical harmonic index. So that can become arbitrarily small. So that's the argument.
Does it become easier for the instability to set in high m or low m? It doesn't matter.
Okay. Now, that's where the physics hits you. Okay? Now you have to ask, and this is kind of where I want to go to, and I want to sketch a little bit for another problem. So now what happens is, you know this system is unstable, and you know it can be unstable at any rotation rate. But you know that stars rotate. So this instability cannot operate, because it would sap angular momentum from the star, and therefore it would stop the star from rotating. So it cannot be that it acts in all stars all the time, because we see them rotating. So what happened? Well, physics happened, because a shorter wavelength, high order m, will be harder hit by things like viscosity, because viscosity is very efficient for short wavelengths, right? And so there will be a balance between when viscosity stops this and when the growth, here it's due to gravitational wave emission, when gravity wins, okay? And that's really the answer.
So the competition between viscosity times scale and radiation reaction times.
Yes, that's exactly right. I'm going to give you some numbers, but for a different case, just to give a flavor. That's what I wanted to get to today. And so there's another fact that's useful, which is, this is the quadrupole m equals to 2 f mode. This change happens at this beta is 0.14 in the real star. But you calculated yesterday the breakup velocity for uniform rotation. It was, as I said, 0.1. Which means for the quadrupole f mode, this change does not happen until you've surpassed the breakup velocity. So that also doesn't happen. So then we know that viscosity can kill you at m. For the quadrupole, it shouldn't happen. Okay? In a Newtonian star, the f mode instability does not act through the quadrupole. It acts through octopole, ellipse 3 and 4. Predominantly 4 is the strongest instability. Now this changes with GR. In GR, that brings the radiation reaction is more efficient, and so then you can bring this f mode instability into play, but it acts very close to that breakup that we calculated. There was an m plus 1 somewhere, so. No, that's right. If you take the quadrupole inertial R mode, which is a current, and we calculated that yesterday, it has some frequency, and you can see that that always satisfies this criterion. Okay? It doesn't have to reach some critical value, it always does that. That's weird. Very weird. In fact, it was completely unexpected, and the result was discovered by complete mistake. And so I should apologize. I did the calculation, I did it wrong. Here's an advice that doing things wrong is not really that bad. I found something that was unstable. I thought it could be this thing, but I didn't understand it. I talked to John Friedman, who said that can't be true. Encouraging. He said, that can't be true, but why don't you go to Milwaukee and we'll talk about it? So I thought about it a bit more. I went to Milwaukee. He and his student, or postdoc Sharon Morsink, had a look at it. They realized that, yes, it was correct. So we agreed that it was correct, and we had to write the paper on this. Unfortunately, I was put, so we agreed I should write the paper, and they would write another paper showing that it was really true. And I had to write the paper saying, here's my calculation, it's all wrong, but the result is true nevertheless, because intuitively you can see this argument I just gave you. it was obvious all along. Okay? And then another part, so that was kind of a difficult paper to write because you wrote a paper you knew was completely wrong, but it shows you something that was potentially important and correct. That happens in life. But later on, the summer that followed, I was visiting Bernard Schutz in his house outside Cardiff. And we were sitting there and we were talking about this, and I said to him, because I'd done some more reading later, and said, do you realize, I said, that in 1978, you were acknowledged by two people that worked on R modes in a paper they did about gravitational radiation in accreting stars. So he had a conversation, and that's the point where you see a famous scientist kicking himself, because he had all the pieces laid out in front of him, and he didn't connect the dots. And I think that's also an example of how, when we focus our minds on this is how it goes, everyone talked about F modes, because F modes are really good at emitting gravitational waves. Nothing else matters. This thing was there all along, right? For 20 years, until a mistake led us back to the beginning. And so I think this tells you a kind of a useful story, that you shouldn't, don't just look at what people tell you all the time. Don't worry about thinking outside the box. Don't worry about asking, well, in some other field of fluid dynamics or cosmology or whatever they did this, can I use it? Could this be true over here? Right? It's those connections, the fluke connections, they come all over and quite regularly. It's just sometimes we make discoveries. We don't want to talk about the embarrassing part of the discovery. I did it by mistake. Okay? That doesn't sound so glorious somehow. You stumble on something. It's better to say, yes, I thought long and hard about this, and then one night it came to me. It says, I made a sign error in the calculation, and then I realized it wasn't wrong after all. That doesn't sound so good, right? So, okay. So what you can do now is we want to ask, how does this balance? Okay? And we should have just enough time to get to a result on that. So what you do is now, you want to ask, how fast does an instability grow? This is always the first question, okay? You have something that's unstable, but if it grows on a timescale of 100,000 billion years, it's probably not going to happen in reality, right? If it happens on a timescale of 1 millisecond, you can be sure it's going to happen. So you have to calculate this, right? It's not enough saying, in principle, it's unstable. A lot of things in the world are unstable, right? Yet they don't seem to fall apart. So this is important. So here, and this is the only case in gravitational wave physics you will be able to say this, I believe. For R modes, we need current multipoles. The current multipoles are leading order. So this is not radiation by deforming the density, it's radiation by having currents swirling around. Okay? I think it's true that this is the only mechanism that is dominated by the current multipoles. So when we started doing that, again, this is something we had never done. Conventional wisdom tells us that gravitational waves come from density variations, end of story. This current multipole is something one writes down and sort of people like Bala calculate because they might need them for some really high order multiple moments that no one ever heard of. Okay? Here, this is leading order, we need to calculate it. It took a little bit of time to get the head around it. Okay? I'm not going to show you what it is. And then, if we also calculate what the energy of the mode is, we have essentially a way of doing that because we have the canonical energy. Right? Or you can take kinetic energy just of the velocities, it doesn't make much of a difference. And then you simply estimate the timescale as saying that whatever energy we've got, we're going to zap with gravitational waves through the multipoles. And then you have to put an absolute value, I guess, because this is going to be negative. Okay? So you take the canonical energy, for example, the current multipole formula that you crank out, put in the velocity field that you calculate for this guy, and then you get a number. And this number is about 50 seconds at, I think, 1 kilohertz. Well, let's do the scaling with that's probably worthwhile. Where is it? Yeah. Spin. So I'm ignoring all the numbers, masses and radii, and they're all canonical, sort of typical neutron star values. It's about 50 seconds at 1 kilohertz spin to a very high power, like this. Okay? That's the spin frequency. Okay? So that's fast. Less than a minute at that breakup velocity. Less than a minute in astrophysics is no time at all. Neutron stars evolve on timescales of thousands of years, millions of years. We could be in play. But we knew from this argument over here that viscosity could be really bad. This is now a convective current. This could be bad news. Okay? So in neutron stars, what people had worried about, so here now what happened was, a lot of the work that had been done over here for the F mode was transported over, adapt this thing to over here and figure out what happened. That's why there was a flurry of activity around 1998, because there were people that already knew how to do all of this. Right? So that was just transport over here. There are two kinds of viscosity. Shear viscosity, which is essentially just particle-interparticle scattering. And the typical number is something like in a neutron star, not surprising, if nothing makes it different, like superfluidity or something. There are many neutrons than anything else, so neutrons crash into one another much more often than they crash into something else. And when you work this out, you get argument, you got the energy, you now have an energy loss from the shear, and so you get a shear viscosity timescale, which is something like 7 times 10 to the 7 times the temperature scaled to 10 to the 9 Kelvin to the squared. Okay? So now you compare these two. This one drives the mode, this one kills the mode, right? 50, smaller than 7 times 10 to the 7. Therefore, the driving wins. Shear viscosity will not stop it at this temperature. If you make the temperature lower, you can ask, at which temperature do I get to be 50? And the answer is about 10 to the 5 Kelvin. Okay? That means real neutron stars, most neutron stars we see have got temperatures between 10 to the 6, 10 to the 7 upwards. So in the real neutron star, this is not going to win at the highest spin rates. Okay? Then there is another kind of viscosity people worry about, which is called bulk viscosity, which is essentially how does the matter react? You push the fluid like this, okay? It's out of equilibrium, chemical equilibrium. Reactions try to push it back to equilibrium on some time scale. So this depends on how much you compress and expand the fluid, okay? So the first estimates that were done for this, for the R mode, were just wrong. Not terribly wrong, factor of sort of 100 wrong. And they were wrong because the R mode doesn't do this very much. It's a current. So this is a higher order effect. And at that time, we didn't know how to calculate this higher order effect. So people just made it up a little bit, okay? And they made it up using logic that applies over here, but actually doesn't apply over here. And so that's why early on you will see a debate about what the bulk viscosity could be, at the end of the day is kind of irrelevant because the number was still never going to be big enough to do anything interesting. Okay? You calculate this, and it's about, for completeness, 2 times 10 to the 11 at, again, frequency dependence, which is the same, squared, and temperature dependence, because the reactions depend on temperature, to a high order. Okay? And again, you see 10 times 10 to the 11 is not smaller than 50. And so again, in this balance, this guy wins. So now what you can do, this is actually exactly where I wanted to go to. You want to say something like this. In general, you can ask, if I put all things together, I get some equation. I don't really know what the ingredients are, but I write it like the energy, the change of the mode, E dot, is going to be something like, I put a minus sign here just to show that it's going to be different, or maybe we should do it like this. The mode, gravitational waves that makes it want to grow, and then all the dissipation mechanisms you can think of, they add like parallel resistors. So shear viscosity, bulk viscosity, anything you can think of can go in here. Okay? So basically what's happened in the last 20 years or so is people have tried to hit us with different things here. Okay? But before we do that, just look at these results, okay, where I've written them. Take a given star, which I've done, and you see that what happens here, you've got something that depends on spin, temperature, spin and temperature. Okay? So I can plot this balance here as a curve in spin and temperature. Okay? And I know that if this guy is shorter, if I'm above the curve, where these balance, then I have an instability. Okay? So typically, this curve looks a bit like this. And this is the 1998 type curve. And it's perfect. So what happened since is a long, long story of various suggestions for why one mechanism or another breaks this, changes this dramatically, probably wipes it out completely. Okay? Because this is a problematic curve, and we'll talk about that a little bit tomorrow, because I'll show you tomorrow how we get gravitational wave estimates for this, and then finish by concluding by looking at some numerical relativity results that also connects with the F mode. Okay? That's where I want to get to. But we can, because this is kind of now nicely set up, we can calculate some gravitational wave estimates and talk about detectability, which I think is a nice place to get to. Okay? But, so what happens here is you can start asking, well, what I can put in other physics mechanisms, okay, than these things. So the first thing that happened was people said, well, one of the first things, let's put in the fact that we've got an elastic crust, okay? What does the crust do? Well, it turns the Coriolis force at the rotation is interesting. It vastly overwhelms the elasticity of the crust. The elasticity is irrelevant. But what could be relevant is the fact that you have a mismatch of the fluid below the crust and above and in the crust. Okay? And that's essentially like the teacup problem. When you stir a cup of tea, why does it stop going around? It's because it forms a little viscous boundary layer very close to the edge of the cup. It's called an Ekman layer. Okay? So people said, okay, we can have this near the crust. And people showed that this is really important, really quite strong. So it lifts this curve up here somewhere. And then people discovered that actually, I'm going to take 2 more minutes, that it wasn't so strong because As I said, the crust actually moves. This is not the teacup problem. This is a sort of wobbling teacup problem where the teacup jiggles about with the fluid. That's not the same problem. So it's a mismatch problem, and you have a penalty factor of something like 100 or something that brings you down because of this mismatch. So that maybe would be the best estimate today for this problem, but I think that answer is completely wrong. And that answer is completely wrong because there is a magnetic field penetrating this, and a magnetic field does not allow that mismatch at all. And so that calculation, I really don't know. Okay? There's a pattern in these lectures. At the end of the day, I don't know. Okay? People talked about hyperons. Hyperons are important here because they can have very, very fast reactions. Okay? But if hyperons were present to a large extent in neutron star cores, because they got fast reactions, they cool the star really quickly. So that goes against cooling data, cooling observations. So observations of cooling neutron stars. So we think the hyperons have to be superfluid. If the hyperons are superfluid, these reactions are slow because the superfluidity stops reactions. So this has an effect, but it's not very big. It's a little bump somewhere. So you can make this a little bit more advanced, but not really. For the F mode, there is a classic paper by Greg Mendel and Lee Lindblom that shows that thing called superfluid mutual friction, which is essentially how the vortices by which a superfluid rotates, which I think you talked about last week, how they interact with the fluid flow. Okay? Essentially electrons scattering off of these vortices. That mechanism wipes out the F mode instability completely. Okay? Because that is very strong. So people say, surely it's going to kill this guy as well. It does not. You have to make the coefficients of this viscosity 100 times or 1,000 times bigger than we think they are to make a big indent in this. And you have to make it that much bigger because of that strong scaling with the spin. Okay? So we don't think this wins either. And then we have the final culprit, which is the magnetic field. And in principle, this could be very important because the magnetic field is very efficient at propagating information. But as I said to you the other day, the problem with the magnetic field in neutron stars' interiors is we don't know what the configuration is. So this is hard to calculate. So my suspicion is that we will fix this problem, remove this instability once and for all, once we understand this problem. But this problem is hard. So what I wanted to do today, I wanted to get to this point, be able to say, look, here's a problem that has a nice mathematical, classical underpinning, starting with the ellipsoid, some really nice but quite difficult mathematics on Lagrangian perturbations, with a rigorous proof of instability, going all the way to physics, some estimates, and then ending up with quite a large number of outstanding questions. And what we learn from this is the more physics you put in, the messier things get. But in this problem, we actually have to do this because we know, if you just take this diagram here, we know quite a number of systems, these accreting systems, again, for which you calculated things, that sit in here. Okay? And according to our understanding, they should not be allowed to be here. But they are. So this story is unfinished. But I'm done. Thank you.